IPsec.
Internet Protocol Security is a protocol suite for securing Internet protocol communications by authenticating and encrypting each IP packet of a communication session. IPsec includes protocols for establishing mutual authentication between agents at the beginning of the session and negotiation of cryptographic keys to be used during the session. IPsec can be used in protecting data flows between a pair of hosts, between a pair of security gateways, or between a security gateway and a host. Internet Protocol Security, IPsec, uses cryptographic security services to protect communications over Internet Protocol, IP, networks. IPsec supports network-level peer authentication, data origin authentication, data integrity, data confidentiality, encryption, and replay protection. IPsec is an end-to-end security scheme operating in the Internet layer of the Internet Protocol Suite, while some other Internet security systems in widespread use, such as Transport Layer Security, TLS, and Secure Shell, SSH, operate in the upper layers of the TCP/IP model. Hence, IPsec protects any application traffic across an IP network. Applications do not need to be specifically designed to use IPsec. Without IPsec, the use of TLS/SSL must be designed into an application to protect the application protocols.
History.
The IPsec working group in the IETF was started to create an open, freely available and vetted version of protocols that had been developed under NSA contract in the Secure Data Network System, SDNS, project. The SDNS project had defined a Security Protocol Layer 3, SP3, that had been published by NIST and was also the basis of the ISO Network Layer Security Protocol, NLSP. Key management for SP3 was provided by the Key Management Protocol, KMP, that provided a baseline of ideas for subsequent work in the IPsec committee. In December 1993, the Software IP Encryption Protocol SWIPE protocol was developed at Columbia University and AT&T Bell Labs by John Ioannidis and others. In July 1994, WIZU at Trusted Information Systems continued this research, which was completed successfully on the BSDI platform after a few months. WIZU quickly extended his development onto Sun OS, HPUX, and other Unix systems. One of the challenges was slow performance of DES and triple DES. The software encryption was unable to support a T1 speed under the Intel 80386 architecture. By exploring the cryptocards from Germany, WIZU further developed an automated device driver, known as plug-and-play today. By achieving the throughput for more than a T1S, this work made the commercial product practically feasible, that was released as a part of the well-known Gauntlet firewall. In December 1994, it was the first time in production for securing some remote sites between east and west coastal states of the United States. The IETF IP Security Protocol was developed starting in 1992 at the Naval Research Laboratory as part of a DARPA-sponsored research project, with openly published drafts by 1993. ESP was originally derived from the U.S. Department of Defense SP3D protocol, rather than being derived from the ISO Network Layer Security Protocol, NLSP. The SP3D protocol specification was published by NIST, but designed by the Secure Data Network System project of the U.S. Department of Defense. AH is derived in part from previous IETF standards work for authentication of the Simple Network Management Protocol, SNMP, version 2. IPsec is officially standardized by the Internet Engineering Task Force, IETF, in a series of request for comments documents addressing various components and extensions. It specifies the spelling of the protocol name to be IPsec.
Security architecture.
The IPsec suite is an open standard. IPsec uses the following protocols to perform various functions. Authentication headers, AH, provide connectionless integrity and data origin authentication for IP datagrams and provides protection against replay attacks. Encapsulating security payloads, ESP, provide confidentiality, data origin authentication, connectionless integrity, an anti-replay service, a form of partial sequence integrity, and limited traffic flow confidentiality. Security associations, SA, provide the bundle of algorithms and data that provide the parameters necessary to AH and/or ESP operations. The Internet Security Association and Key Management Protocol, ISAKMP, provides a framework for authentication and key exchange, with actual authenticated keying material provided either by manual configuration with pre-shared keys, Internet Key Exchange, IKE Indicative 2, Kerberized Internet Negotiation of Keys, KINK, or IPsec DNS records.
Authentication header.
Authentication header, AH, is a member of the IPsec protocol suite. AH guarantees connectionless integrity and data origin authentication of IP packets. Further, it can optionally protect against replay attacks by using the sliding window technique and discarding old packets, see below. In IPv4, the AH protects the IP payload and all header fields of an IP datagram except for mutable fields, that is those that might be altered in transit, and also IP options such as the IP security option, RFC 1108. Mutable, and therefore unauthenticated, IPv4 header fields are DSCP2S, ECN, flags, fragment offset, TTL and header checksum. In IPv6, the AH protects most of the IPv6 base header, AH itself, non-mutable extension headers after the AH, and the IP payload. Protection for the IPv6 header excludes the mutable fields, DSCP, ECN, flow label, and hop limit. AH operates directly on top of IP, using IP protocol number 51. The following AH packet diagram shows how an AH packet is constructed and interpreted.
Encapsulating security payload.
Encapsulating security payload, ESP, is a member of the IPsec protocol suite. In IPsec it provides origin authenticity, integrity and confidentiality protection of packets. ESP also supports encryption-only and authentication-only configurations, but using encryption without authentication is strongly discouraged because it is insecure. Unlike authentication header, AH, ESP in transport mode does not provide integrity and authentication for the entire IP packet. However, in tunnel mode, where the entire original IP packet is encapsulated with a new packet header added, ESP protection is afforded to the whole inner IP packet, including the inner header, while the outer header, including any outer IPv4 options or IPv6 extension headers, remains unprotected. ESP operates directly on top of IP, using IP protocol number 50. The following ESP packet diagram shows how an ESP packet is constructed and interpreted.
Security association.
The IP security architecture uses the concept of a security association as the basis for building security functions into IP. A security association is simply the bundle of algorithms and parameters, such as keys, that is being used to encrypt and authenticate a particular flow in one direction. Therefore, in normal bidirectional traffic, the flows are secured by a pair of security associations. Security associations are established using the Internet Security Association and Key Management Protocol, ISAKMP. ISAKMP is implemented by manual configuration with pre-shared secrets, Internet Key Exchange, IKE Indicative 2, Kerberized Internet Negotiation of Keys, KINK, and the use of IPsec DNS records. RFC 5386 defines better than nothing security, BTNS, as an unauthenticated mode of IPsec using an extended IKE protocol. In order to decide what protection is to be provided for an outgoing packet, IPsec uses the Security Parameter Index, SPI, an index to the Security Association Database, SADB, along with the destination address in a packet header, which together uniquely identify a security association for that packet. A similar procedure is performed for an incoming packet, where IPsec gathers decryption and verification keys from the Security Association database. For multicast, a security association is provided for the group, and is duplicated across all authorized receivers of the group. There may be more than one security association for a group, using different SPIs, thereby allowing multiple levels and sets of security within a group. Indeed, each sender can have multiple security associations, allowing authentication, since a receiver can only know that someone knowing the keys sent the data. Note that the relevant standard does not describe how the association is chosen and duplicated across the group. It is assumed that a responsible party will have made the choice.
Modes of operation.
IPsec can be implemented in a host-to-host transport mode, as well as in a network tunnel mode.
Transport mode.
In transport mode, only the payload of the IP packet is usually encrypted and/or authenticated. The routing is intact, since the IP header is neither modified nor encrypted. However, when the authentication header is used, the IP addresses cannot be translated, as this will invalidate the hash value. The transport and application layers are always secured by hash, so they cannot be modified in any way, for example by translating the port numbers. A means to encapsulate IPsec messages for NAT traversal has been defined by RFC documents describing the NAT-T mechanism.
Tunnel mode.
In tunnel mode, the entire IP packet is encrypted and/or authenticated. It is then encapsulated into a new IP packet with a new IP header. Tunnel mode is used to create virtual private networks for network-to-network communications, for example between routers to link sites, host-to-network communications, for example remote user access, and host-to-host communications, for example private chat. Tunnel mode supports NAT traversal.
Cryptographic algorithms.
Cryptographic algorithms defined for use with IPsec include HMACSHA1 for integrity protection and authenticity, CBC for confidentiality, AES-CBC for confidentiality. Refer to RFC 4835 for details.
Software implementations.
IPsec support is usually implemented in the kernel with key management and ISAK and PIKE negotiation carried out from user space. The openly specified PF key management API, version 2 features often used to enable the application space key management application to update the IPsec security association stored within the kernel space IPsec implementation. Existing IPsec implementations usually include ESP, AH, and IKE version 2. Existing IPsec implementations on Unix-like operating systems, for example Sun Solaris or Linux, usually include PF key version 2.
Standard status.
IPsec was developed in conjunction with IPv6 and was originally required in all standards-compliant implementations of IPv6 before RFC 6434 made it only a recommendation. IPsec is also optional for IPv4 implementations, but due to the slow deployment of IPv6, IPsec is most commonly used to secure IPv4 traffic. IPsec protocols were originally defined in RFC 1825 through RFC 1829, which were published in 1995. In 1998, these documents were superseded by RFC 2401 and RFC 2412 with a few incompatible engineering details, although they were conceptually identical. In addition, a mutual authentication and key exchange protocol, Internet Key Exchange, IKE, was defined to create and manage security associations. In December 2005, new standards were defined in RFC 4301 and RFC 4309, which are largely a superset of the previous editions with a second version of the Internet Key Exchange standard ICAV2. These third-generation documents standardized the abbreviation of IPsec to uppercase IP, and lowercase sec. ESP generally refers to RFC 4303, which is the most recent version of the specification. Since mid-2008, an IPsec maintenance and extensions working group is active at the IETF.
Alleged NSA interference.
In 2013, As part of the Snowden leaks, it was revealed that the U.S. National Security Agency had been actively working to insert vulnerabilities into commercial encryption systems, IT systems, networks, and endpoint communications devices used by targets as part of the Bull Run program. There are allegations that IPsec was a targeted encryption system. The OpenBSD IPsec stack was the first implementation that was available under a permissive open-source license, and was therefore copied widely. In a letter which OpenBSD lead developer Theodore Raupt received on December 11, 2010 from Gregory Perry, it is alleged that Jason Wright and others, working for the FBI, inserted a number of backdoors and side-channel key leaking mechanisms into the OpenBSD crypto code. In the forwarded email from 2010, Theodore Raupt did not at first express an official position on the validity of the claims, apart from the implicit endorsement from forwarding the email. Some days later Raupt commented that "I believe that NetSec was probably contracted to write backdoors as alleged. If those were written, I don't believe they made it into our tree." Jason Wright's response to the allegations: "Every urban legend is made more real by the inclusion of real names, dates, and times." Gregory Perry's email falls into this category. "I will state clearly that I did not add backdoors to the OpenBSD operating system or the OpenBSD crypto framework, OCF. This was published before the Snowden leaks."
IETF documentation. Standards track.
RFC 2403, the use of HMAC MD5-96 within ESP and AH, RFC 2404, the use of HMAC SHA1-96 within ESP and AH, RFC 2405, the ESP does CBC cipher algorithm with explicit for, RFC 2410, the null encryption algorithm and its use with IPsec, RFC 2451, the ESP-CBC mode cipher algorithms, RFC 2857, the use of HMAC Ripent 160-96 within ESP and AH, RFC 3526, more modular exponential, MODP, Diffie-Hellman groups for Internet Key Exchange, IKE, RFC 3686, using Advanced Encryption Standard, AES, counter mode with IPsec encapsulating security payload, ESP, RFC 3947, negotiation of NAT traversal in the IKE, RFC 3948, UDP encapsulation of IPsec ESP packets, RFC 4106, the use of Galois counter mode, GCM, in IPsec encapsulating security payload, ESP, RFC 4301, security architecture for the Internet Protocol, RFC 4302, IP authentication header, RFC 4303, IP encapsulating security payload, RFC 4304, extended sequence number, ESN, addendum to IPsec domain of interpretation, DOI, for Internet Security Association and Key Management Protocol, ISAKMP, RFC 4307, cryptographic algorithms for use in the Internet Key Exchange version 2, ICAV2, RFC 4308, cryptographic suites for IPsec, RFC 4309, using Advanced Encryption Standard, AES, CCM mode with IPsec encapsulating security payload, ESP, RFC 4543, the use of Galois message authentication code, GMAC, in IPsec ESP and AH, RFC 4555, ICAV2 mobility and multi-homing protocol, MOBIC, RFC 4806, online certificate status protocol, OCSP, extensions to ICAV2, RFC 4835, cryptographic algorithm implementation requirements for encapsulating security payload, ESP, and authentication header, AH, RFC 4945, the Internet IP Security PKI profile of ICAV1/ASAKMP, ICAV2, and PKIX, RFC 5996, Internet Key Exchange Protocol version 2, ICAV2.
Experimental RFCs.
RFC 4478, repeated authentication in Internet Key Exchange, ICAV2, protocol.
Informational RFCs.
RFC 2367, PF Key Interface, RFC 2412, the Oakley Key Determination Protocol, RFC 3706, a traffic-based method of detecting dead Internet Key Exchange, IKE, peers, RFC 3715, IPsec Network Address Translation, NAT, compatibility requirements, RFC 4621, design of the ICAV2 mobility and multi-homing, MOBIC, protocol, RFC 4809, requirements for an IPsec certificate management profile, RFC 6071, IPsec and IKE document roadmap.
Obsolete RFCs.
RFC 2401, Security Architecture for the Internet Protocol, IPsec Overview, obsolete by RFC 4301, RFC 2409, the Internet Key Exchange, RFC 4306, Internet Key Exchange, ICAV2, protocol, obsoleted by RFC 5996, RFC 4718, ICAV2 clarifications and implementation guidelines, obsoleted by RFC 5996.